Hello students, welcome to the digital classes. Today we will discuss electricity. Now we use electricity in our life in many ways. Just imagine if there is no electricity for 1 hour. If there is no electricity for 1 hour, we can't see TV, you can't watch this digital lesson, there won't be fan or AC, no grinder and other appliances, but overall there won't be much impact on life. Now just imagine if there is no electricity for 1 day, there won't be water in taps, no charge in mobile phones, no drinking water, no storage in fridge because fridge requires electricity for cooling, and patients in hospitals in ICU will be at risk. Now just imagine if there is no electricity for 1 month, what is going to happen? Most of the goods will be running out of stock, no stock of various goods, there won't be TV, mobiles and communication, no water because all water is run by motors when we draw water, there won't be internet banking and other internet services, there won't be emergency services too, and ICU in hospitals will be very difficult to be functional. So now if we imagine that there is no electricity for 1 year, it almost appears that the life becomes a standstill. It appears that life comes to a standstill. So we can understand that without electricity our life would be very difficult. Electricity is part and parcel of our life. In this video, the speed of the fan is increased by turning the knob. What exactly is happening inside these wires and fan? This is another video where we see that the volume of the sound is increased and decreased. Children, so those who are in a position to get up, you can get up and turn the switch of the fan on and then change the speed. Quickly do that. Have you done it? Yeah. Just by turning the knob of the fan, you are able to change the speed at which the fan is running. So what exactly is happening inside? What are we changing? How are we controlling the speed of the fan? So in this chapter electricity, we will discuss how these machines are controlled, also what exactly makes a fan run, and not only in these videos, we encounter many situations where we see how we control machines just by using electricity. Now not only in our day-to-day life, we find electricity in our body too. There is electricity in our body too. Electricity in our body. Our heart needs electricity to pump blood. To run, walk, jump, lift objects, we need electricity because muscle contraction is an electrical process. To see, we need electricity. In the eyes, the image is converted to electrical signal and sent to brain. To think, we need electricity. Our brain produces electrical signals and sends to various organs. So there is no life without electricity. Electrical signals in our body travel at around 200 meters per second. We can do an activity to observe the reflexes which happen due to electrical signals from brain to hand. Children, let us do an activity in which we can find the speed of the reflexes. Now, we can understand that the coordination between body organs depends on electricity, that is on electrical signals that travel through neurons, that is the nerve cells. Now, children, here is another activity where we can see what exactly happens in the wires. We need a battery, cotton threads and a bulb. We connect all of them and see that the bulb does not glow. Now, we replace these cotton threads with copper wires and now the bulb glows. Let us repeat the same activity, but without the bulb. Here we connect wires and bulb and we remove battery from the circuit. We see that the bulb does not glow. This is an activity to test conductivity of materials. For that, we need a bulb, a fan, a battery, wires, cotton thread and a metal spoon. First, let us connect the battery to the bulb and fan through wires. Let us connect the battery to the bulb through the wires. We see that the bulb glows and the fan runs. Let us use a cotton thread to connect the battery to the bulb. We see that the bulb does not glow. This is because the cotton thread is not a conductor. Now, let us connect the battery to the bulb using a metal spoon. We see that the bulb glows and the fan runs. This is because the metal spoon which we use is a conductor. All metals are good conductors of electricity. The bulb does not glow when cotton threads are used because cotton threads are insulators. They do not conduct electricity. Also, when battery is removed, there is no source to supply electrical energy and hence the bulb does not glow. Children, now let us replace cotton wires with a spoon and let us see what is going to happen. We take a metal spoon and then check if electricity is conducted. So, here we replace copper wire with a spoon and we see that the bulb glows. So, the bulb glows now because the metal spoon which we used conducts electricity. So, there are some objects which conduct electricity and there are some substances which do not conduct electricity. All those who conduct electricity are called conductors. Conductors have free electrons. These free electrons move carrying the electrical energy. This is called electric current. Here is a list of some conductors and in this all are metals except carbon, which is a non-metal, and this is the only non-metal which occurs naturally that conducts electricity. Electric current is an ordered motion of electrical charges. In case of metal wires, the charges are free electrons. Electric current is defined as the amount of electric charge passing through a cross section in 1 second. So, the amount of charge that passes through this area in 1 second is called electric current. We can measure by using the formula. Electric current is equal to amount of charge flown through a cross section in unit time. So, the formula will be I is equal to Q by T. The SI unit for current is ampere, which is coulomb per second. So, we define electric current as the amount of electric charge passing through a cross section in 1 second. Let us do a numerical now. Find electric current if 30 coulomb charge flows through a cross section in 1 minute. Electric current is given by amount of charge flown by time, which is equal to Q by T. charge is 30 coulomb and time is 1 minute, that is 60 seconds. We have to convert everything to SI units, and so current is equal to 30 by 60, which is equal to 0.5 ampere. In the previous activity with copper wires and a bulb but no battery, let us connect a bulb. We see bulb does not glow. Here battery is not used, hence there is no source of energy. A battery supplies electrical energy by maintaining constant potential difference across the ends of the wire. Here are some batteries of various sizes. Here are some more batteries. Many of them are button cells which are used in watches, remote controls and other electronic gadgets. Here is a battery which is used in a car. Just like an object rolls down from a greater height to a lower height, the charges also flow from higher potential to lower potential. So, just like an object rolls down, if there is difference in heights, electric charges move if there is difference in potential. A battery maintains potential difference across the wire. How does the battery is able to do that? A battery consists of two metal plates and a chemical. The metal plates are called electrodes and the chemical is called electrolyte. An electrolyte will have positive and negative ions. Based on the reactivity of the ions, there will be a chemical force that drives the ions towards the metal plates. Positive ions will be driven to one plate and the negative ions will be driven to the other plate. So, here the chemical force makes the positive charges drive towards the right side plate and hence the plate acquires positive charge. The positive ions in the electrolyte get accumulated on one electrode. We call this electrode as anode due to the chemical force. The negative ions in the electrolyte get accumulated on the other electrode. We call this cathode. Now, an electric force is developed between the plates because of the accumulation of charges. This electric force will try to make the charges move in the opposite direction, and in equilibrium, when these two forces are equal, the movement of charges will stop. So, whenever we buy a new battery, the electrolyte inside the battery will be in equilibrium. So, there will be some charges which get accumulated on the positive terminal and there will be some charges which get accumulated on the negative terminal. And suppose if we connect these two terminals by a wire, then the electrons, the free electrons in the wire will try to go towards the positive terminal. So, when we connect a wire from positive to negative terminal through a bulb, then the electrons in the wire starts flowing. So, here we see the electrons move towards the positive plate. So, how many electrons are entering into the positive terminal? Those many electrons from the battery come into the wire, and then we call this as electric current. So, if there is a bulb in the wire, it glows. If there is a fan, it runs. The work done by the chemical force to move 1 coulomb of charge from positive terminal to negative terminal is given by W by Q, which is equal to force times the distance by Q. This is called potential difference. In other words, it is called EMF, electromotive force. Electromotive force is the work done by the chemical force to move 1 coulomb charge from positive terminal to the negative terminal of the battery. So, a battery will maintain constant potential difference across its terminals. Because of this, whenever we connect these two terminals by a conductor, then the charges start moving in the wire. So, this constitutes electric current. Here is a symbol for a cell, and if we have more than one cell, we can call it as a battery. That is the symbol for a battery. Here we can see in the battery there are many cells. Each compartment is one cell. So, there are 1, 2, 3, 4, 5, 6 cells which are connected in series to form a battery. Children, Now, whenever we connect any conductor across a battery, what happens is the current flows in the conductor, and this current will be directly proportional to the potential difference which is applied by the battery. You apply a greater potential difference, there will be a greater current. This was observed by George Simon Ohms. So, children, let us do an activity by which we can understand the relation between the potential difference and the current. For that, we need a battery, ammeter, voltmeter, a wire and a bulb and a switch. So, we have to connect a battery, wire, ammeter, switch as shown in the figure, and voltmeter connected across the iron spoke, and then we should start applying different potential differences and then measure the current. The ammeter measures the current, the voltmeter measures the potential difference. For different values, we get different values of current. As we increase the potential difference, the current increases. Let us note them down in the table. From this activity, we can understand that the ratio of voltage to current is constant. This was observed by George Simon Ohm, and hence this law was framed. Ohm has given this in the form of a law we call Ohm's law. The current in a conductor is directly proportional to the potential difference applied across the conductor. So, we have current I proportional to V, that is the potential difference, and removing the proportionality sign, we write I is equal to V by R, or V is equal to IR. Here R is the resistance of the conductor. For all the conductors which obey Ohm's law, the graph will be linear. For the conductors which do not obey Ohm's law, the graph will be non-linear. Now, let us solve a numerical. Find the electric current if 10 volt is applied across a conductor whose resistance is 50 ohm. Current I is equal to V by R. Current is equal to 10 by 50, which is equal to 1 by 5, which is equal to 0.2 ampere. Children, let us do an activity to observe the reflexes which are based on the electricity that flows in our body. So, here is a small activity to observe the reflexes. What you have to do is ask your friend to keep the hands like this, and you have to drop a card between those hands, and you should ask your friend to catch. You ask your friend to keep the hands apart, and you have to drop the card and your friend has to catch it. Let us see if it happens. Watch it. It is quite difficult. Closer, and you have to drop a card. Again, again. Children, so what happens is, whenever we see anything or any object, the light travels into our eye. From there, inside the eye, the image of the object or anything whatever we see will be converted into electrical signal. It goes to the brain. From the brain, then there will be an electrical signal which will be passed down to your hands, so that we act accordingly. So, all this happens in a very small time. This is in the form of electricity. All the signals which pass from your brain will be through nerve cells, will be in the form of electricity. They travel at around 200 meters per second. Also, many of the people will tell you that if we suffer an electric shock, we will not be able to move our hand. This is because, suppose if I touch anything and then there is electricity which is passing into my hand, what happens is the electricity, because of an electric shock, will be very high. So, there will be lot of current which is passing into our hand, but at the same time, because of reflexes, our brain tells us the hand to remove it, but the muscles here will not be able to identify that signal, because the signal which is coming from the brain is a very small electrical signal, and the current which is coming from the wires into your hand is more, and hence the muscles are not able to identify the signal from the brain, and hence will not be able to remove it. And that is the reason whenever people suffer from an electric shock, they will not be able to move their hand or body till they die. Children, we see that the birds which are sitting on the wires, they do not suffer electric shock. In these pictures, you see many birds which are sitting on the electrical transmission lines, and they are not at all suffering any kind of electric shock. Why do you think so? Have you ever wondered, have you ever thought about it, that how come a bird is not suffering an electric shock? This is because they are sitting on the same wire. When they sit on the wire, the potential difference between the 2 points where they sit on the wire is same, and hence there is no electricity that passes through the bird, and hence it will be safe. Children, now let us revise. We have seen that electric current is defined as the amount of electric charge passing through a cross section in 1 second. Electric current is equal to amount of charge flown by time. I is equal to Q by T. The SI unit for current is ampere. Just like objects roll down if there is difference in heights, electric charges move if there is potential difference, and batteries maintain potential difference across the wires. The work done by the chemical force to move 1 coulomb charge from positive terminal to negative terminal is given by W by Q is equal to force times distance by Q. This is called potential difference, which is also called EMF. EMF is electromotive force. Ohm's law. The current in a conductor is directly proportional to the potential difference applied across the conductor at constant temperature. I is equal to V by R. R is equal to resistance of the conductor. Children, we have come to the end of the session. What I want you to do is observe various devices, appliances, and also the specifications given behind the appliance. That is, they may write how many volts it requires, or how much of current it draws, or how much of power it dissipates, or how much of energy it consumes. Also, next time you get electricity bill, just observe it, and then we are going to discuss in the further classes how electricity bill is made, or how electricity bill is calculated, how much of current is drawn by various appliances, which appliance will draw more current, which appliance will draw less current. All these things will be discussed in the next classes. Thank you.